Hello, everybody. All right. Well, good morning, everybody. Just to let you know where we are, we will have another quiz Friday. I don't know if I would call this a quiz or a test, but we won't have class again on Friday. This will be a completely multiple choice um, quiz, and it will be over both chapter 25, which is nuclear chemistry, and the electrochemistry. It is open book, but it's not open internet. So while you can use your book or have whatever resources you want there, I would like you to do it without any electronic resources. The other thing I'm going to attempt to do, just as a trial, and I will send out a series of emails about this, is I would like to do this exam with the Respondus and the Lockdown browser. The main reason I am doing that is because our final exam, I need to see if that will work for that. Now, in order to use Respondus, you have to have a webcam. If there's somebody here who doesn't have that, I will have to set up a different version of the quiz. So when you look on there and you see there's two different quizzes on there, I don't want you to panic. Um, I really would like to be able to have everyone use the Respondus, but if you cannot, you need to let me know before Friday at 10. And as I found out through a couple students, no, if you don't have a webcam, you just can't take it without the webcam. I'm trying to figure out how to set that up, and if I do that, I will let you know. Um, but again, the main reason I want to do that is the final exam. Um, our rights to the final exam being online require the use of a lockdown browser. If I can figure out how to just do the lockdown browser and not have to do the webcam thing, I will do that, but I don't know whether I can do that or not. So plan on using that. Look for emails from me between now and Friday. The Respondus and everything setting that up is going to take about 10 minutes. So please do that before class starts on Friday. I know if you're in um, Gen Bio, Gen Bio, you've probably already done that. But anyway, and how many questions is the quiz? That's a good question. And if I had it written for sure, I would be able to tell you. Right now, I've got about 70 questions, and I know that's too long. So I am looking for somewhere in the range of, I would say for an hour test, 25 questions ish, somewhere in that range. But I don't know that for sure. You will have a specific time limit for this quiz. And are there any other questions about the quiz before I move on to that? And yes, you will have some things over chapter 25 on it. Again, some of them are really simple. You can probably look some of these up in your textbook and only take about 3 times longer than if you just did it yourself. So I would do that. I will be collecting a couple questions out of chapter 25, and I will post those, which ones I'm collecting after that. Chapter 25 is the last homework I will collect. There will be no other homework in this class. And as I have been trying to download things to grade it, uh, with a lot of the people who had submitted pictures for homework, I was able, I'm able to download, and some of them are taking like 5, 10 minutes a piece to download. So that's why I'm having trouble like getting to the homework grades on there. I have started looking through the take-home exams, and I realized, later on that I had just put 10 points on the uh, equilibrium, and I think it said 10 points score will be added to exam two, and I counted it as 10 points per question. I'm not going to go back and change that. So you're welcome. No, I have not gotten through the entire class, but when I do that, I will do that with exam two. I will also get the curve to exam one up there, and have the calculations for the class accurate on Canvas. My goal is to have that by the end of the week. My original goal was to have that by this morning, but I spent a significant part of this morning with no internet here, and Canvas requires an internet connection. So I had fun with that. Can you explain what we are supposed to do for this week's lab, please? Yes. It would help if I posted the lab. Again, the problem with posting the lab was I had some severe internet trouble, and when I tried to upload a couple videos, they're just still uploading. I plan on having those for yesterday, but the lab that we're doing this week is going to be an atomic absorption lab, and I'm actually making it next week's lab with this week off for lab because of the problems that I've had. I will still try to get that on there today. But again, it might not be there. So there will be no lab. We have one more lab left, and that's a flame atomic absorption. I have a good video with that, with the data on it. I don't know about the quality of the video, but the quality of the information is good. And I will have that. It will help if you want to prepare that to read through the flame atomic absorption lab. What you will see is me doing the lab. And you will have to take that data and put it into the lab spreadsheet, which again, I started uploading that yesterday, and as of when the first outage that I had, it hadn't uploaded yet. So I'm just fighting with upload issues a little bit. And that's, I guess, to be expected when you take an area, out in the country like we are and flood it with extra users during the day. So that's part of the problem. Let's see. And what about the lab that's due tomorrow? If all the people have not put in their data yet, go ahead and do it with the data that is there. Since evidently I haven't checked the spreadsheets to see if the data is in there, go with whatever data has been collected at this point. I will go ahead and move that due date till Friday at midnight, so you have a little bit of extra time on that, if that's okay. If you look at there and it says that it's due, whenever I said it was, and it shows that it's late, don't worry about it. As long as it's in Friday by end of the day, I will count it on time. Actually, I'll go ahead and make it Sunday into the day. Okay, how's that? Let's see. So I spent a fairly large amount of time so far just talking about what we're going to do for Friday. Now, I'm going to do something a little different today. I am going to go ahead and go through a little bit of PowerPoint things, and I'm going to share my screen with you. I will go ahead and move my camera up here, and then I will move it back to the screen at the end of the class. But there are some things that I want to show you. And again, this will be recorded. Hopefully it's recording. Yes, it's recording now. So I'm going to share the screen, and then I'll move the camera around a little bit so that you can see me. Okay. So if you are having trouble seeing my screen, somebody let me know in the chat. Otherwise, I am hoping you are seeing the nuclear chemistry that we see here. All right. And this chapter is on nuclear chemistry. I'm not going to go through the entire book's PowerPoint, but there's a few slides that I want to point out and a few that I'm going to spend time on. I will put this on the, the Canvas site. All right, and now I have to get this started. Okay, come on, mouse. Okay. All right, let's see. All right, so here we go. So nuclear chemistry. So supposedly, there we go. I clicked it about 100 times here. Just a little bit, I thought I would put this on here. It's kind of an important bit of data here. You know, protons are positive. Look at the mass of the proton. Look at the mass of the electron. Now, these masses are important when we're using Einstein's equation, E equals mc squared. And what's interesting is if I add up all of the masses, so in other words, if I have like an oxygen atom, it's not going to be the mass of 8 protons and 8 neutrons and 8 electrons. There's actually some of that mass goes into an energy called binding energy. And we'll be talking about that here in a little bit. I'm not going to do the calculations for that, although it's important to know that these calculations are relatively, you know, simple plug into equation calculations. I'm more concerned that you are aware of what happens to that. Mass is converted into energy or binding energy. Energy is converted into mass. And that same energy and mass relationship can happen in nuclear reactions. Okay. Just to remember what isotopes are. Okay. Let me move that off to the side. There we go. That should record better now. Okay. So isotopes are atoms of the same element but different mass numbers. For example, boron 11 and boron 12. There's 2 different ways that we indicate that, by putting the boron with the 10, the boron with the 11, or putting our mass numbers at the upper left of it. These show the difference. Now, both of these are stable isotopes, okay? With radioactivity, I can't talk about radioactivity without talking a little bit about Marie Curie. And she was the one who isolated and characterized radium and polonium. And, you know, from 7 tons of uranium, she was able to get a single gram of radium. Now, what's interesting is Marie Curie and her husband, Pierre Curie, did a lot of research. Pierre Curie also discovered radiation poisoning. He carried a lump of radium around in his pocket for luck. And I would be willing to say, you know, it did bring him luck, but I'm not sure it was the good kind. But they learned a lot from it. Marie Curie is one of the greatest chemists or physicists of all times. I'm not sure. I'm going to make a comment here. Is studying the nucleus chemistry or physics? The answer is yes. Now, for some reason, there is this artificial division between chemistry and physics. And if you go to the smallest of the small particles, all the way up to the subatomic particles, and even the nucleus, that's physics. Now, if you take, you know, electrons, protons, and neutrons in the nucleus, that's chemistry. So the atom is a borderline between chemistry and physics. Then if you get larger than a single atom, suddenly physics isn't really concerned that much with the interactions there until you get to a very large quantity, and that's moving around. So if you're taking, you know, anywhere from a, you know, single atom to a mole of things, that range is the range of chemistry. And there. All right. And let's see. I am hearing that there are some people with internet that's kind of unstable today. That might be me. So if I start cutting out or whatever, feel free to put it on the chat that there's some trouble with it. I am fairly confident this is recording well on my computer because I don't have to have an internet connection for that. So I will post this afterwards. All right. The symbols for natural radiation, this is straight out of the book, alpha, beta, gamma. I just wanted you to see a gamma that I didn't write here. That's the whole reason I did that. When you look at that and you're looking at my gamma, you look at my gamma and you just think, why? Just because that's kind of what it looks like when I do that. Okay. Again, the charge, the mass is interesting. Now notice the gamma radiation has no mass. It is just energy that has been converted. Okay. From mass. All right, penetrating ability. I talked about this a little bit. Alpha particles can be stopped by paper, beta can be stopped by a centimeter of lead, and gamma particles require at least 10 centimeters of lead. Yeah. The greatest energy is the gamma radiation. The lowest energy is the alpha radiation. but the alpha radiation has a relatively large mass and is able to do much more damage. So its momentum is much greater than that of the other. Okay, this is one of the things that I wanted you to look at. I thought about writing all of these decays and everything and going through that. This is where we were talking about uranium-238. Now, when uranium-238 decays, it starts by an alpha decay, then a beta emission, then a beta emission. So notice we go from U-238 to U-234. This is 10 to the 9th years. That's a billion years or more, okay? Then we get into some reactions that occur in days or minutes, you know, and this is like 10,000 years for this to start decaying. So we see some additional decays as it goes along in here, all the way till we get to lead-206, which is stable. So from U-238 to lead-206, we have a series of decays that are there. And you can see some of the reactions that are occurring. Notice 238 here, 234 and 4, sum of the mass numbers is the same, the atomic numbers is the same we see in the other reactions. Those are reactions that I'm going to expect you to do on Friday. There'll probably be at least 2 or 3 questions where I give you a reaction. Instead of all of the pieces there, I will put a question mark, and you will have to match up with the correct particle. And hopefully all the formatting is going to work out okay on these questions, but just in case the formatting does not work out, I will have Zoom open and I will have my email ready to go to answer your questions, even though you're probably not going to be able to ask them on the lockdown browser. If you need to pick up your phone and text me a question, that's fine. Please do not text each other during this time. I know there's no way that I can stop that except for the fact that I will have the respondents with the webcams. Just do your own work, please. Okay. Other types of nuclear reactions, we have positron emission, so we can emit a positron from the nucleus. Okay. So in that case, the atomic number goes down. We can also have an electron emission. Okay. One of the problems that I have you doing is calculating the energy that is released when an electron and a positron annihilate each other. It's kind of a fun little calculation. Okay. All right, the stability of nuclei is kind of where it's important for us to look at today. Hydrogen is the most abundant element in the universe. It represents 88.6% of all atoms. Helium represents another 11.3% of the atoms. So together, 99.9% of all atoms and 99% of the mass of the universe is in hydrogen and helium. Okay, so are we sure of that? Absolutely, we're as sure of that as we can possibly be without leaving this planet, which is to say, from what we can tell from this planet, this is what the universe is like. Here is the band of stability I was talking. Notice for very small things, a ratio of neutrons to protons of 1 to 1 is in the stable range. As you get larger, you need to have more protons and neutrons. Okay, so if I get something in this range down here, I expect to have an alpha emission to give a lower atomic number. Over here, if I'm up in this range, I expect to be a beta emission. And down here, we might expect a positron emission or electron capture. Okay, so you can use this to help figure out what is likely to occur. I am not going to ask you on the test which type of reaction is going to occur on this. I will ask you about fission and fusion, but we'll get to that here in a second. All right, the binding energy, I just went through, the book had a couple slides on it, and I thought, oh, I'll just leave those in. So for deuterium, which is 1 neutron and 1 proton, if I take a look at the proton and the neutron and the mass of the hydrogen atom, I can find the binding energy per nucleon for this. Okay. Now, if I take the mass of the proton, the mass of the neutron, and the mass of these two added together, our difference is 0.00239 grams per mole. And using Einstein's equation, E equals mc squared, I can calculate the energy per mole and the binding energy. And this is how binding energy is calculated. Okay. What's more important is to kind of look at the region of the greatest stability. Notice that iron 56 is at the top of the stability. So if I have particles larger than that range, I will tend to have a nuclear reaction where fission is going to occur. Atoms are going to split apart. If I have smaller ones, there's going to be fusion. So examples, we will look at in fusion, we have the reaction occurring in our sun. For fission, we have the U-238 decay that we talked about. We also have other reactions that can occur in nuclear plants that are fission reactions. This is where we get our nuclear energy. Okay, radioactive decay. This is the equation out of the book. I prefer to use N over N0 because that's how I learned it. However, A is activity in disintegration per time, and you can do activity or number of atoms. Decay follows first order kinetics. Remember, if we have our half-life, we can find K. Okay? Radiocarbon dating. Willard Libby got the Nobel Prize in chemistry for developing carbon-14 dating. Here's the apparatus that he used. Okay, so you don't really have a good picture of the apparatus, but I didn't have to do anything to get rights for this particular PowerPoint to be able to present it. Okay, so I went through this reaction. Nitrogen reacts with a neutron in the atmosphere to give carbon-14, and that carbon-14 is oxidized to carbon dioxide, and when a plant dies, the carbon-14 is not replenished. So we look at the decay of carbon-14 with a half-life of 5,730 years, and we can use the activity of a sample to date the sample. Now, in case you're wondering, is the amount of carbon-14 in the atmosphere the same? It's fairly constant. Notice the percent change from the 19th century value that we have in the amount of carbon-14 in the carbon-14 in the atmosphere. Yes, there are some areas of higher or lower range, but being able to adjust to that, we can be pretty accurate on our carbon dating up to about 7,000 years ago. And even up to close to 100,000 years ago, we can have some accurate carbon dating. If you get beyond that, you'll have to use some other things such as uranium dating. There is also some potassium reactions that we can look at the date of something with as well. And that's how we date rocks. Okay, we actually don't date rocks. That would be kind of silly. But anyway. And just because I have to share a joke, you know, I used to have a pet rock, and my pet rock sat up on my shelf. And one day I came in and my pet rock was on the floor in pieces. And I came to the conclusion that my pet rock had committed suicide because everyone was taking him for granted. He was nice. People who know anything about a little mineralogy or rocks will find that one funny, or at least I find it funny. Okay, nuclear fission. Now, there's a couple things that we need to understand about nuclear fission. One of the big things that we're going to see is that a reaction usually occurs with a collision. Now, sometimes we have atoms that spontaneously decay. In the case of U-235, U-235 is stable enough, it really doesn't decay unless it gets hit by a neutron. And when that gets hit by a neutron, we get this unstable nucleus which then flies apart. And notice I have 2 daughter nuclides and 3 neutrons that are going out here. So notice that 1 neutron is coming in, 3 neutrons coming out. What that means is if I have enough U-235 there and I start that reaction, it can go uncontrollably into a chain reaction. 1 reacts with 3, reacts with 3, and notice these little things are indicating a fairly large amount of energy occurring or released in this reaction. Okay, so a chain reaction has three general steps: the initiation, the propagation, and the termination. And if we just have a critical mass of uranium-235 present, it's going to be an uncontrolled chain reaction, also known as a nuclear bomb. So how do we get nuclear energy? Well, I'll talk a little bit more about nuclear energy when I get through this PowerPoint. But what happens is they put control rods in there that absorb some of the neutrons. So we don't end up with a chain reaction, but we have a continuous reaction. Okay. And there are nuclear plants that run for, 50, 60 years. They're theoretically capable of running for hundreds of years without shutting down. No, none of them have done that. And we'll talk about nuclear waste here a little bit too. Okay. The units for measuring radiation, most of you really need to know that these exist and that you can look them up if you have to. But you should be familiar. If somebody talks about curies, it's disintegration per seconds. And a becquerel is a disintegration per second. A curie is 3.7 times 10 to the 10th disintegrations. No, don't memorize this. Now, the important ones for people are rads and rems. Now, a rad measures the amount of energy absorbed. And a rad is 0.01 joule absorbed per kilogram of tissue. And a REM is what is known as a Röntgen equivalent demand, and it's based on the amount of type of radiation. REMs are generally what we can measure radiation that people are exposed to in. And it kind of gives an idea of tissue damage. And we usually measure it in millirems. And doses from 0 to 25 millirems, there's no effect observed. Once we get into larger doses, small decreases in white blood count. Here we see, they're saying 500 REMs is death for virtually or almost 100% of the population. I actually work at Argonne National Lab, which is the lab that came about from the Manhattan Project in Chicago before they moved to Los Alamos to actually test it. And they had a lot of interesting things there. There are people who are who got a what is it called, a fatal dose of radiation that lived, and there were people who got very small doses who had severe effects from it. So radiation affects people differently. That's why you can't say, well, if you get 10 REMs, you're in trouble. Well, you might. 10 REMs may be enough to kill you, and 500 REMs might not be enough to kill you. Every person is different. You don't want to find out. Now, I will tell you, the people that I only met one person who was exposed to a really large dose, and he survived it. He shouldn't have survived it. Now, the question is, did he really get that big of a dose? We don't know. We do know that he was potentially exposed to huge amounts of radiation and lived from it. All right. Nuclear medicine is really important, and it uses a lot of radioisotopes. There's a couple things that happen there. One is we can put a nuclear substance somewhere in your body to be able to follow things around and see what's happening. For example, we can use radioactive iodine to test things in the thyroid. The other thing is we can use radiation directly. That's one of our treatments for cancers. And then finally, we can use, some of this like X-rays and such like that for imaging. Now, you've also heard about MRIs. MRIs are magnetic resonance imaging. The MRI comes from something called the nuclear magnetic resonance. And what's interesting is there's no actual nuclear reaction with the NMR. It just looks at the interaction of radio waves with the nucleus. But that's something that you can look at in a future class. Here are some common radioisotopes. Again, note I mentioned the thyroid one. There's some other things that we can look at. I'm not going to spend a lot of time on this, although nuclear medicine is extremely important. And I have a feeling there's going to be a lot of advances in the next 20 years using some nuclear medicine. And they're going to find out that some things weren't worth the risk that they were using. All right. So this is the end of the PowerPoint. I do want to go through just a little bit more about nuclear energy, but I'm going to stop and set up my camera first on my board. Good shot of my ceiling there. Let's see if I can stop the screen sharing and get back to here. Okay, need to adjust this just a teeny bit. Adjust one more thing here. All right, so the last thing I want to talk about today is a little bit about whether we should be using nuclear energy and what are the problems associated with nuclear energy. And I don't have an answer for you, but I do have a lot of information for you. One of the big things that we need to realize is that, you know, we're getting all of our energy from nuclear energy. Most of it's from fission in the sun, okay? And you can look through those reactions for the sun, hydrogens combined to end up giving you helium. And it's not a single reaction that occurs. The sun is in a plasma state, and that's so high energy that the electrons and protons are not connected to each other. In other words, the nuclei are free to run into each other. That's how nuclear reactions can occur so easily. Okay. Now, there's a couple other things that we need to talk about with fission. First of all, nuclear reactors. Are nuclear reactors safe? Well, obviously, you have heard of Chernobyl and the Fukushima areas where bad things have happened. Now, there's two different types of things. In the case of Fukushima, there was an earthquake followed by a tsunami, and all kinds of problems happened from that. With that, there were still, I mean, that was bad, and it increased the background radiation of the Earth quite extensively. The other one that was really bad was Chernobyl. Now, Chernobyl was bad because there were a number of safeguards in place, and some things went wrong, and untrained people were at the nuclear plant. And had they done nothing, it wouldn't have been near as bad as what they did. So what they did is they shut down some things. And I don't have all the details, but they shut down some of the safety systems. Oops, that's what happened. So the first thing we've got to do is, if we are going to have a nuclear reaction, we need to have everybody involved in it trained to do their job and trained well. The second thing is, you know, do we have it safe from things like tornadoes or whatever? Because can you imagine a tornado in Kansas hitting a nuclear reactor? Well, they actually did imagine that. And a lot of the nuclear reaction, you think of the big cooling towers that they have, but you also see this big dome. Now, I have one of the guys I did one of my master's degrees with, he worked at a nuclear power plant, and he was actually involved with it when they built it. And what's interesting is they come in and they build this huge, they use lots of steel, concrete, and everything. And the people who are involved in the industry call it BERT. BERT stands for Big Expensive Round Thing. Okay, and this is the containment building for the nuclear reaction. The nuclear reaction is actually occurring down in here. And in order to test that, they did a few things. One of the things they did was they measured in here the seismic effect when they flew a 747 into it. And it was relatively safe at that point. So think of the nuclear reactor. The reactors are safe. They have been tested with 747 attacks, you know, flying a plane into them. Okay, so there's a lot of precautions going into making it. This last thing that we got to deal with is, okay, so we have a safe place to do this nuclear reaction. We have this nuclear reaction. But what do we do? Because when we have a nuclear reaction, there's waste. And what do we do with that nuclear waste? Now, currently, this is what we do with the nuclear waste. There's a little room inside of BERT where they put the nuclear waste. Okay? Now, what's the problem with that? Well, for the majority of the nuclear waste is still kept on the site at the place where it was produced. So what do we do with that? Now, I was involved in actual research that took the volume of nuclear waste. So we would take a container this big, actually extract all the radioactive elements from it, be able to use a significant amount of it and reduce it into a much smaller volume. That smaller volume then undergo what we call vitrification. And the vitrification is basically putting this in with some stuff and making it into a glass. So it's basically a solid. So it's not going to run out of its container. Now, if your half-life is 1.5 billion, 4.5 billion years or something like that, this isn't something we want escaping from its container. And the idea is to put it in certain places where it's in a subduction zone, so where it's not going to be forced out of the earth, but if it goes anywhere, it's going to be forced into the earth. That's an idea that we can do with it. Now, has that been done? No, at least not to my knowledge. What happens is that we get this nuclear waste and nobody wants it driving through their state. Nobody wants to say, oh, here, let's put it in a mountain in my backyard. So we now have these large containers of waste at the sites of the nuclear reactors. So is that a good or a bad thing? And the answer is no. It's a problem that is going to have to be dealt with. Fortunately, nuclear reactors do not produce a huge amount of nuclear waste, so we have some time before we can get to it. There are also breeder reactors that use a lot of the nuclear waste for the fuel for the nuclear reaction. The big problem with the breeder reactors is they also produce fissionable plutonium, which can be used for nuclear weapons. You don't have to use it for nuclear weapons, but because it's capable of producing nuclear weapons, there's a lot of controls on it, and we could make reactors that produce way less waste. Now, here's the other thing. We are converting mass into energy, and we're releasing that energy into our atmosphere. Is that contributing to the warming of our planet? That's a good question. I don't know about that. I do know that the energy goes from mass to energy and it goes somewhere, okay? That energy is released, just like the stored up energy that we have in fossil fuels. That energy is released. And does that have an effect on our environment? Yes. Do we know the effect of that? A little bit. No, we don't have a complete understanding of our atmosphere, of our planet, and how everything works. We're getting closer. We might now be, at the point where we can say we know a percentage or two of everything that affects our environment. We don't have a complete understanding yet. So should we follow the precautionary principle and not use nuclear reactors? Well, maybe. The problem is we have nuclear reactors. So is it more dangerous to continue using the nuclear reactors or to just shut them down and let them sit there? You're going to have the same amount of radiation there. So that's a big question. Fun questions for us to deal with. All right. So with that, that is our nuclear chemistry. I know I spent a good, day, almost 2 days on it. And that's all. And yes, it's going to be on the test on Friday, although, okay, I'm calling it a test, calling it a quiz. I don't know. The reason I call it a quiz is because that's what Canvas is calling it. It will be all multiple choice. It is going to be a preview or a trial run for our final exam. So I want you to be able to make sure of that. The final exam is still going to be the time scheduled. That final exam you will have 1 hour and 50 minutes for. I will plan on opening it up about 2 minutes early and letting it go 2 minutes late. So you'll have 1 hour and 54 minutes. Expect somewhere around 70 questions for that. And yes, they will be multiple choice. And theoretically, they are going to be closed book, although I will tell you right now that I will allow you to use the periodic table provided by the American Chemical Society and the periodic table we used in my class. Both of those will be there. You'll be allowed a calculator, and you will do that. in order to take the final, you're supposed to have the Respondus in the lockdown browser. And again, if you have trouble with that, I need you to email me that you're going to have trouble with that soon so that I can figure out how to deal with it. Unfortunately, I can't just like give you a paper copy of the final exam, which would be much easier on my part, and give you a Scantron form and have you do it. The advantage is, as soon as you submit it, you will know what your score is on the final exam. You won't know what the grade will be, but you'll know what your score will be. I will have to do some statistical analysis in order to determine what percentage that is going to go into the grade book. So when you first look at the final exam, you're going to see that it doesn't appear as a grade. So I'm going to take that grade of your final exam, put it through basically a formula, and calculate a percentage from that. And that's how that's going to work. Am I going to upload the Chapter 25 PowerPoint? Yes. I planned on uploading it this morning, and I had no internet. So it will get there. If you are looking for it and it's not there, shoot me an email, because, you know, I have to upload it, and then I have to make sure to publish it so that you can see it. I have, like, on a consistent basis, sometimes it doesn't upload. Sometimes I just forget to make it available for people because I can see it. So it doesn't dawn on me that you can't see it. So if there's something that you want on Canvas that I said is going to be there, please let me know. All right. What kind of things will be on the quiz on this Friday? Okay, electrochemistry. I expect you to determine the cell potential. And there's going to be several reactions where you have a cell potential. I will ask questions about, will this reaction occur spontaneously? In other words, is the cell potential positive or negative? I may even have a Nernst equation one in there, but they will all be multiple choice. I will also have nuclear reactions on there. There'll be several of those because I think they're easy. Hopefully you think they're easy, where I'm going to say, what is the missing particle here? And you will have to go through and figure out what that missing particle is. There will be a few questions on radioactive decay. I will go ahead and have at least 1 or 2 half-life questions where you're going to need to use there's at least one that's going to use that. I might do 2 that will do that. Now, be aware, I can ask half-life questions that are more conceptual and less mathematical. Expect to have about 5 calculation questions on this, and the rest are going to be either the nuclear reactions. I don't count those in the calculations, even though you do simple calculations. And so you will have, what is the missing element, or what is the missing particle here? There'll be several of those. There will be electrochemistry questions, and there will be some generic questions over nuclear energy, radioactivity. I might even have some simple questions about what different terms around the nucleus mean. And also a couple questions maybe. Now you remember I went back to that one on where it showed iron 56 as the peak of the stability. I would ask a question, would you expect this particle to undergo fission or fusion? That's a type of question I might have. Now, you're probably wondering, how am I going to get 4 choices out of that? Well, if you know me, you can kind of figure that out. If not, I don't think it's going to be that difficult. Please, on this one, do not overthink all of the questions. I know some of you are really good about reading the question and trying to make them significantly harder than they are. I do think, okay, I've got to have 4 or 5 questions that I think are fairly tough on here. About 4 or 5 that I think are going to be ridiculously easy, and you should be able to get those just because you can open your textbook. And the rest are going to be, if you understand what's going on, they're fairly simple questions. May not be easy, but they'll be simple. So that out of the 25 or so questions that I'm going to have, that's what it's going to be like. Okay. All right. Is there a difference between electrode potential and cell potential? Um, Not exactly. There's not really a difference. So when we talk about electrode potential, generally we're talking about a particular half cell. So half cell potential and electrode potential are the same. Cell potential is generally the combination of the two cells that we have there. I will make it clear on the exam which one I'm looking for. Okay. Um, how will an e-textbook work with a lockdown browser? I don't know. I haven't figured that out yet. Um, so it's going to be open note. You can have stuff printed off. Again, just because it's open now. I will not be upset if you have two electronic devices, your computer, where you're taking the quiz on one, and if you happen to have another device. Now, this might not be the best thing to have your book open on, but if this is the only way you can have your book open on that, do that. If you need to have your textbook open on your phone, because that's the only way you can have it, please just shoot me an email and let me know that. That way I'll know if you're looking on your phone when you're taking the exam. I'll know what that's for. What is the best way to study for the quiz? I would say the best way to study for the quiz is to review chapter 19, the electrochemistry, and to do the, at least make sure you know how to do the homework questions out of chapter 25. Again, I'm not going to collect the chapter 25 until after the quiz. That I'll probably take those up through Monday, end of the day. And that'll be the last thing. And that's the best way to study for it. Now, again, that's also person to person is going to be different. First thing I would do is I would get the equations and have them all written down like these equations. I would have them just sitting right there. You can even use the periodic table that I provided that's got some of these on. So make sure you know where those equations are. Make sure you know the Nernst equation and have it in whatever form you like to use it, and be able to substitute in for that. When you get to the electrochemistry questions, yes, I'm going to have a question like which element is oxidized or which element is reduced, or what is the oxidation half reaction that's going on here. You need to be able to identify those. Those will be some of what I think are the simplest questions. All right, do I have any other questions on the quiz or on homework? I will tell you right now, in doing the take-home exam, I got through about half of the class on getting your exam 2 points added to it. So if you're in the later half of the alphabet, that has not taken effect. I think I have Canvas calculating grades correctly. I think. But I don't think I have all the grades correctly in Canvas. So that's what I'm going to spend a significant amount of time tomorrow doing. Or today, I will have from 11 to 11:40, I will have office hours. I'm going to take a break in between now and then. So if you have questions, feel free to come back during that time. And if you don't have questions, I will just be sitting here with Zoom open on one computer, and I will be on another computer theoretically uploading some things, although I may not be able to do that with Zoom open, which is also why I'm going just 11 to 11:40. So seeing no other questions, I will hopefully have this recording up later today for those who had connection issues. And hopefully the connection issues weren't here, although I've had quite a bit. So with that, have a good day. Oh, one other thing. You might start getting emails or something about course evaluations. Please go ahead and do those course evaluations, at least the number part of it. If you don't want to spend any time on the comments, that's fine. But please go ahead and do the course evaluation. And in your course evaluation, please, if you need to say something about how bad I am doing Zoom presentations or whatever, go ahead, but realize this is not what I signed up for when I started to teach this class. So I'm trying to do the best I can with it. And, sitting here teaching in my basement brings back days of when I was in Heimerman. Heimerman, the first floor had one window and that was in a closet. So I feel like I'm back in a dungeon sometimes when I'm working here. Because if I tried to teach upstairs where all my kids are going around, I don't think we would get much. So, if you can, be nice when you're giving that. Will I have other office hours if people have class at 11? Yes, I will email that out. Theoretically, I am going to have office hours tomorrow from 1:30 to 2:15. However, I have a meeting that is scheduled at 2:30 that I just realized the people I'm meeting with are on the East Coast. So I don't know if it was 2:30 here or 2:30 there. So as soon as I figure that out, I will email tomorrow's office hours to everyone. Okay, and that'll be tomorrow afternoon. If you need to ask questions at another time, feel free to say, hey, I can't meet during that time. Can you put office hours during this time? And I will make an attempt to do so. All right. With that, good day, everyone.